Good. Once more, thanks to Dustin and Paula for the invitation. I'm going to talk today about classical laws of motion on shape space. And as I just mentioned, it's part of my PhD thesis under supervision of Professor Detlef Dur and Professor Peter Pickel. Unfortunately, Detlef Dur has passed away, and it's a real sad event that took place in our work, our research group. We missed him a lot. Last time, about half a year ago, I gave a similar talk when he was present, and he was making nice comments about the talk. And when I was preparing this talk once more, I could remember his comments, and it was a bit, for me, emotional to again prepare the same talk with those thoughts. But I mean, that's life. I mean, he went at the top, yeah, and he was one of the. It was one of the things which was important for him to stay at the top, and he would always remain in our hearts. Okay. Let's go to the talk. So we are going to have a talk about the difference between Newtonian ontology in physics and Leibnizian ontology in physics. Julian gave a nice explanation of the differences. I just summarize very briefly the main differences for the people who are a bit maybe less familiar with the differences, but the majority, of course, they know all the differences. I mean, in the Newtonian ontology, as he was introducing and he was promoting in his book and writings, he assumes that there exists some three-dimensional entity, space, and there exists some flow of a river. He was saying these words in his book, that it flows without any respect to movement of material, and these entities, absolute entities, which are immaterial entities, so to speak, they are the background upon which you put the matter. And the matter in his theory are, of course, the good old points like particles matter. And Leibniz, at the same time, he was criticizing this way of doing physics because he was saying, Leibniz was saying, observationally, all you observe are the relative positions and the relative times, and you don't see those absolute entities really from a practical point of view or from an observational point of view. And Leibniz was saying, if you want to make physics, to do good physics, you should start with more sensible, observable entities, and those are the relative positions of the particles. And the same with the passage of time. The passage of time, you should see how you measure passage of time, and it is always by some clock, and the clock is just the motion. Yeah, you use one motion as reference motion, and you say other particles are doing this and that when this reference motion is there. So this is the summary of the difference and the dispute between these two distinguished thinkers, and the dispute went on for many centuries and has not yet settled down completely. I mean, we are, of course, as a relationalist, more in favor of Leibnizian ontology. Good. I just put some facts here, trivial facts. Fact number one is that the textbook Classical and Quantum Mechanics have Newtonian ontology. Everybody knows that. And the fact number two is that classical and quantum mechanics have very accurately verified empirical predictions and give quite clear explanation for occurrence of numerous natural phenomena. And the fact number 3 is about us. We think relational ontology introduced by Leibniz should be adopted in physics. There are many reasons for this fact 3. I don't give the philosophical reasonings, the physical reasonings, but the writings of Julian Barbour, Ernst Mach, and many other big thinkers. You can find many good, sensible arguments why it is reasonable to think that relational ontology is good. Yeah, it's something that you can work with it. And there seems to be a contradiction between point 2 and 3. So if the best theories we have are all based on a Newtonian ontology, how could it be that we insist still on Leibnizian ontology? I mean, aren't we blind to the fact that classical and quantum mechanics are working so good? I mean, it is possible to have both 2 and 3 together, fact 2 and fact 3 together through what we call principle of relationalism. Yeah, I would explain that in the next slide. If a theory with Newtonian ontology satisfies this principle of relationalism, it can be recasted into an empirically equivalent theory with Leibnizian ontology. So in this sense, it is just different readings of the nature. Then you can read the nature through Newtonian ontology, or you can read the nature through Leibnizian ontology. And what is principle of relationalism? I mean, for everybody who is a relationalist, this statement is a trivial thing. Yeah, two possible absolute configurations of universe differing from each other just by a global similarity transformation are observationally indistinguishable. With the word observationally, I mean kinematically and dynamically indistinguishable. And if you are a relationalist, I mean, this is what you believe in. You don't even give a name to it. Yeah, that's the starting point. And if you aren't a relationalist, I mean, you may think that there is one or another experimental violation of this principle. Yeah, I mean, we are not aware of any violation so far, but you may think that in the future there would be some experiment or some phenomena which signifies absolute scale and which signifies the difference between the two configurations of the universe, which are similar to each other, which are connected to a similarity transformation. You would think that such a difference, experimental difference, would pop up in the future if you are a convinced Newtonian. But I mean, we are not among those physicists. So does classical and quantum mechanics satisfy this principle of relationalism? I mean, if you just look at the potential energies which appear in classical and quantum mechanics, you would see obviously that these are not scale invariant potential. They are translation invariant, they are rotation invariant, but clearly if you change the distance of two matter points, so matter points like particles, particle 1 and 2, you would see that potential changes, and of course the derivative of potential would be the force, and the normal reading would be that the force changes, and the principle of relationalism already is clearly violated here. I mean, at first sight, the answer seems to be negative. Should we then give up implementation of principle of relationalism classical theories? Before we answer this second question, we should ask another question. Do we already know everything about classical theories like Newtonian theory of gravitation or electromagnetism? Do we know everything about that? The answer to this question is no. In many aspects, we don't know everything about that. But for me, the most important aspect, which is relevant for our work, is that no derivation of the value of G from logical foundations of Newtonian theory of gravity has been found so far. The value of G in a given unit system is only empirically determined. Yeah, and this is a foundational gap in Newtonian theory, which makes the theory an incomplete absolute physical theory. In a complete absolute physical theory, you would give a function or you would give an argument based on ontology of Newtonian theory, how why the value of G is what it is. As long as you don't give that, there is something to explain. You know, it can be a coincidence that the value of G is what it is. And this is a point that many people have questioned in the past. Yeah, and one of the clearest protests against lack of research about the value of G and other constants of nature was Albert Einstein himself, which has a nice correspondence about the how you should classify theories. But I don't go now to the works of Einstein. So we take advantage of this fundamental gap for implementation of principle of relationalism in classical theory. Yeah. I mean, the current value of G as measured is this one. Yeah. Imagine you have access to some absolute units of length and time. Yeah. And imagine they now coincide with SI units. Yeah, SI units are some practical units which are in principle relational units. You have a meter stick in I don't know, in Paris somewhere, and you have some atomic clocks, and you just define SI units by the meter stick, for example, in Paris, and the frequency of the cesium atom. But we are saying, if you are a Newtonian, you don't think that these are all about units. You think that there is also some absolute unit. If you believe in absolute space, you also believe in absolute units of length, which is something immaterial, because the absolute space in this sense is immaterial. But now we are having this change of view from Newtonian view, which you believe that you have these absolute entities in the world, to the Leibnizian view. And if you believe in Newtonian view, then you can say at some moment of time, my relational units are coinciding with my true absolute units. Yeah, and imagine that's the case for the time being. Then perform a scale transformation on the whole universe except your absolute units. Yeah, on the whole universe, I mean material universe. So you take the position of the particles, how do you call it? The interparticle positions. You would multiply them with some constant number c. Yeah, c is any positive number. Then we are saying that the Newtonian gravitational potential remains invariant if the G also would be multiplied by the same number C. Yeah, that's a possibility. Yeah, if that in the new universe in which you have made all the interparticle distances bigger, you also change the value of G to CG. So you are making the gravity, so to speak, stronger in the bigger universe. But wouldn't this change the, I mean, with this, you would make the gravity, of course, a scale invariant, but wouldn't this change the balance of forces in nature? I mean, you can't just make the gravity all of a sudden stronger and keep all other forces in nature, the strength of forces, constant. That would violate principle of relationalism, because I mean you can then compare the strength of forces in the bigger universe to the smaller universe, and with the change of the strengths, relative strengths of the forces, you can detect in which of these two universes you are finding yourself, in the smaller one or in the bigger one. So if you let gravitational constant move, change like this under a scale transformation of the universe, of the material universe, you should also take care that the relative strengths of the forces remain constant. And the relative strengths of electromagnetic force to, for example, to weak force is given by this formula. You know, there are ways to derive that. And the relative strength of gravity with respect to weak force is given by this formula. If you change G, you can say if you multiply G by C, in order to do not change the ratio of weak force to gravity, you should also change h bar, Planck's constant, with C. And if you change h bar with C, you should, of course, change epsilon 0 with 1 divided by C. This C is by the way, should be capital C, is the velocity of light. Yeah, the other C I was speaking is the changing of a scale of the universe. So if you want to keep the relative strengths of the forces constant, you should do all this transformation at the same time. Yeah, if you change, if you make the universe, the material universe, bigger, you should also change the value of G, H bar, and epsilon 0 as this written here. So in some future complete absolute physical theory, G, H bar, and epsilon 0 would depend on a scale of the universe. In other words, they are being homogeneous functions on configuration space. G and H bar being homogeneous of degree 1, and epsilon 0 being homogeneous function of degree -1. Yeah, we don't have access to real functions. Yeah, this is just if you would have a complete absolute theory, you would have a derivation of these G, for example, from matter distribution or other constants, which we don't know where they come from as an option from matter distribution. It could be some other distribution, I don't know. But all we are saying that if principle of relationalism wants to be how do you call it, to be valid, those functions should have this transformation property. That's all the restriction we have, and we have no idea what kind of functions at the end they would be, but we don't need that for our purposes. Good. What happens with measurement units? I mean, you always have the measurement units to define before measuring a quantity. And there are many different kinds of units used in physics. And the best units, for many reasons, one of them is for their universality, are the Planck's units, which are being derived from more or less laws of nature themselves, the constants which appear in the laws of nature. And these are the formulas for the derivation of a set of units which Max Planck himself introduced. And these are the values. If you put the correct values of all the constants here, you would get a set of units, Planck units. And then we said, I mean, if you have these two universes, one of them is bigger than the other one by a factor c. Yeah, again, this c happening here is a speed of light. And the other C I'm speaking about is the change of the scale of the universe. If you perform a universal scale transformation on material universe with a factor C, you would see that with the transformations that we saw on last slide, that LP, so the units, Planck units of length becomes c times bigger, Planck's units of mass becomes itself, and Planck units of time becomes c times bigger. So we are seeing that this one is of course intuitive, yeah. And this one says us that the time units in the new universe is different from the past universe. So the time is getting dilated, so to speak. You are seeing a dilation of time here. And practically both units of time and length get dilated by the same factor c. Remember that g has had this value currently in these units. The units in which the value of g is expressed gets also scaled by a factor c. So even though in the fixed absolute units we had g goes to c times g, the value of g remains constant in internal units. Internal units are the Planck's units in this case, yeah. And that is, of course, it should be like that, yeah. You see, if the value of g wouldn't be the same as in the smaller universe, then by just measuring g, you could say in which universe you are finding yourself, and that would violate the principle of relationalism. So you see, those transformations we had before takes care that all the measurements would give you the same results by changing appropriately the measuring units. And the next question we are going to discuss is, how do velocities transform under dilations? Yeah. I mean, the definition of velocity from high school or from elementary school is that it's distance passed divided by the time that it takes to pass the distance. And in order to, okay, I should explain it with an example. So you are an experimenter, you shoot a particle, you want to measure its velocity in your laboratory, and you do it twice. Once you do it in the smaller universe, then you scale the universe bigger. You also, of course, become bigger. The distance become bigger. Everything, the time units become different, bigger. You see that the result of the measurements in the bigger universe would be the same as the result of the measurement in the first universe. So yeah, all the experiments you do to measure the distance, how do you call it, to measure the velocity of some particle would result in the same numerical value. Yeah, principle of relationalism and the characteristics of Planck units together are responsible for this equality. By the way, the characteristics of Planck units are themselves consequences of principle of relationalism. So in that sense, just the principle of relationalism gives you these results, that the velocity measurement in the new universe would give you the same numerical values as in the smaller universe. So that the number of ticks of internal clock during a process or an experiment is independent of the absolute scale of universe is justified by principle of relationalism. Yeah. I mean, it is being used here. I said that if you are in the bigger universe, your clock is also, your clock does not show a different number of ticks, but each tick of the clock would become dilated. That's why you have a C delta T here. And this delta T is the same as the delta T before, because if it was not before as the same delta T here, you would violate the principle of relationalism. Or you could say that I am in the bigger universe or the smaller universe. Okay, this enables us to introduce a metric on shape space in a natural fashion. So I'm going to explain first how the metric on internal space is being introduced. Internal space is the means the quotient space of the configuration, absolute configuration space with respect to the Euclidean group. So you take the absolute configuration and you take away the translational degrees of freedom and the rotational degrees of freedom. Then the reduced configuration space, we call it, people call it in the literature internal space. Yeah, and if you have a metric on center of mass configuration space, which is the mass metric, yeah, this is the metric on QCM. And I hope that most of the people are familiar with the notation. So if you put a u here, you mean it's a velocity on the configuration space. Yeah. So it means that you have a velocity of particle 1 to particle n. And v is another vector which is a tangent to some point of the configuration space, center of mass configuration space. And this is the how you have the metric. Yeah, this is the mass metric. And the mass metric, you as you see, it is has the good property that it is rotation invariant, in the sense that if you go from configuration x to configuration gx, of course you should transform the velocities accordingly, and the velocity transformation of velocities is just you take the representation in that dimensional space, and then there are known representations of SO3. Yeah, then you would get a new vector here and a new vector there, and then if you compute the distance between those two, you would get a number which is the same as the number before. That's why you say the mass metric is rotation invariant. So cos m is a rotation invariant, SO3 invariant metric. It reduces uniquely to a metric on B. B is, by the way, the internal, the metric B is the metric on the internal configuration space. We don't call it M anymore, yeah, with another letter. And now, given two internal vectors, v prime and u prime, are two vectors tangent to the internal configuration space at point Q. There are unique vectors u and v, so that P is the projection from configuration QCM, from a center of mass configuration space to Q internal. So by the projection, Px goes to Q. So X was one of the points on the configuration space, which is above the fiber. Maybe I just try to. Oh, okay, I cannot write it here. You should have the fiber bundle picture in your mind. Many people are familiar with that. The reduced configuration space Q int is the base space, and QCM would become the total space, and the fibers are the SO3 fibers. Yeah, from one point Q, you would go to many points on the fiber which are projecting down to the same point Q. And then this projection, if you have the push forward of the projection, it's a mapping. That's why you can also define the push forward mapping. Push forward takes the tangent vectors of the configuration space and brings it to tangent vectors to the internal space. Yeah, and these are how the vectors on configuration space are related to the internal configuration space. I mean, for people who are familiar with differential geometry, these are trivial things, and if you are not familiar with that, I don't have time to explain it in details. But these are the relations that you have. Yeah, you project down a configuration to an internal configuration. You can push forward under this projection a vector on configuration space to a vector on internal space. and these are the new vectors you would get. And the metric you define on internal configuration space is through this defining equation. You just take the u, which you call the lift of the u prime, and you get the v, which is the lift of the vector v prime, and then you just compute it from the mass metric you had. Yeah, and to which x you are lifting a point q, it doesn't matter, you know, because metric m was SO3 invariant, so to which x on the fiber above q, the internal vectors u and v had been lifted, would not make any difference for the value designed by bq to these two vectors, v prime and u prime. That's how you get a metric on internal space. Yeah, and let me go. And now we want to have the same procedure and have a metric on shape space. You know, we of course start with some Vx. It's some vector on center of mass configuration space. Yeah, so you already have reduced the absolute configuration space with respect to the total translations. In other words, you are going to the center of mass reference frame. And then if you do a scale transformation, so if you make the configuration bigger by a factor c, we already spoke how vectors should transform under a scale transformation. Yeah, under a scale transformation, the vector vx goes to a vector vcx. Vector vx means that this entity is a member of the tangent space to the point x of the configuration space, and this is another entity different from this one. This is a tangent. This is a member of the tangent space to the point cx. So mathematically, it's a different entity, but the components it has are the same components you had there. Yeah, and those are because here you put the velocity of the particles. In particle system, you have n three-component velocities, and we have seen that the velocities are being measured by measuring instruments, and we saw that in the new universe you would assign the same velocities to all the particles. So under a scale transformation, a vector vx goes to itself. Yeah, it's like an identity transformation. You can say it, and that's because of the experimental justification being considered here. So hence the mass metric is a scale invariant in this sense. So if you have if you have mx, vx, ux, you do a scale transformation of the universe, you go to mcx, vcx, ucx, and the value you get here is the same as mx, vxx. That is what we mean by mass metric on its own being a scale invariant. To say it more precisely or more mathematically is that using internal units like Planck units for coordinatizing configuration space brings the mass metric m in a scale invariant form. And these Planck units are not just magic. These are internal units. Yeah, if you want to coordinatize configuration space, you better use real coordinates which you have experimental access to it. And if you use experimentally available coordinates, then you would see that that m on its own is a scale invariant. And the same story as before for the internal. Oh, I should hurry up. I think I have 15 minutes left. So the metric n of the shape space can be written or can be defined through this defining equation. It's identical to the previous one. Yeah, you can have this definition, and I just set another slide about the meaning of horizontal vector, because these things, I mean, you start with v prime and u prime, which are two vectors on shape space, and then you need to lift them up two vectors u and v, and how to lift the vector to the total configuration space. There are many ways to lift the vector to the total bundle space. From all those ways, we take a horizontal lift. Yeah, there is a unique way which is being called horizontal lifting. And this, I mean, for people who are in differential geometry, I don't need to explain horizontal lift, what that means. But for other people, I just try to say it very quickly. Don't blame yourself if you don't fully understand, because I'm giving too much information in a very small amount of time. So in order to have to define horizontal lifting, you always define in a fiber bundle setting a connection form. Yeah, and the connection form we define on the total configuration space is the addition of two smaller connection forms. One of them is for the rotations. The other one, we have developed this connection form through direct analogy with the rotational direction form. This is known in the literature, and this one we have derived it through analogy with the rotation one. And these are operators. Yeah, you have these operators which act on the tangent space of the total bundle space. And dx, which you see here, is another operator which goes from a real number to real number. And it is defined through this equation. Lambda dot here is the scale velocity, so to speak. It's a real number. Yeah, if you have dx of lambda dot, you would get the scale momentum. Yeah, that is what also in the works of Julian Barbour and his colleagues, they also have, I think, the same expression for a relation between a scale velocity and a scale momentum. I mean, we call this dx dilational tensor. Yeah, and lambda dot stands here for the rate of change of a scale of the system, a scale velocity, so to speak. And I have a bold lambda dot because there is a difference. If you have a lambda as a scale variable of the system seen from absolute space, you can of course see the scale of the universe. For example, imagine you are the God, you are looking at the universe, you can of course see the scale of the universe, and that scale of the universe is this small lambda. That's a scale degree of freedom, so to speak. And this lambda is the relational quantity that you take the change of lambda dot divided by lambda. It's a bit complicated to imagine this as a relational quantity, but I have some other place I would explain how you could understand it as a relational velocity. But never mind. And the lambda, you could have many different scale variables. One of the possibilities, just take the two most distant particles in your whole universe, in your whole system, and take that distance as a scale variable of your system. Good. Let me go to the, so that is the, how do you call it, the connection form on total configuration space. Oh, I should have said, I mean, with the connection form, the usage of connection form was that if you have some vector on total configuration space, you apply connection form on that vector. If the answer becomes 0, that vector is horizontal. And this gives you a clear mathematical identification of what kind of vector is horizontal and how you do horizontal lift. You know, that's just remarks why I explained those connection form. Okay, now we are going to explain about, talk about equations of motion. Yeah, we want to know how motion of a system, how the equations of motion on shape degrees of freedom look like. I mean, the mass metric on QCM expressed in these coordinates, S are the shape degrees of freedom. There are 3n-7 of them. Lambda, as I explained, is the scale degree of freedom, and these are the Euler angles for the orientation degrees of freedom. These are not, of course, you are having some absolute frame in mind, that you can define these. And then if you write down the mass metric in those coordinates, it becomes of this form. You have some n alpha beta, which n would be the metric on shape space on its own, and then you have this for the scale, and then you have this one for the rotational velocities. This is the decomposition of the metric in those variables. By setting the instantaneous unit of length to lambda, one gets the following expression for metric. If you say, for example, at the moment lambda, you set you want to go to internal units of length. That's why you set lambda equal to 1. That's one of the options you have. And then now all of the Ri and A, which are here, of course, you should re-express them in these new units, which could be expanding length units. You never know. So provided the above metric, we are ready to write down the Lagrangian of the system, Lagrangian of classical mechanics. I am going to be a bit faster so that I stay in time. So this is the expression of Lagrangian, which is the kinetic part, which we saw before, with some v, and v in this time is just a function of s. So the Newtonian potential, all the potentials we have in classical mechanics, with those transformations of constants of nature, we made them scale invariant vectors, scale invariant potentials. That's why they are all functions of just s and not any other variable. And then, of course, from this Lagrangian, you already can read off the dilational momentum is the dl d lambda dot, is this one which coincides with the other formula we had before. So this is another derivation of that formula. As the Lagrangian is now scale independent, D is now a new conserved quantity. So in this, you can call it modified Newtonian theory or modified classical mechanics. D is a conserved quantity. That's its difference from the normal Newtonian mechanics, which Julian and his collaborators work intensively on that. Now, okay, and we want to have the equations of motion here. And the problem is that these velocities happening, appearing here, these are what people call quasi-coordinates. These are this is in a non-holonomic reference frame. Means that you cannot have there are not real coordinates on configuration space whose derivatives are these variables. These are not directly derivatives of the three Euler angles. These are non-integrable combinations of the three Euler angles. That's why they are being called quasi-coordinates or quasi-velocities. There is and there is a whole formalism, beautiful formalism, how you derive Lagrangian equations of motion in non-holonomic reference frames, and those are known with different names, but the most popular one are the Boltzmann-Hamel equations of motion. And if you work the mathematics, I mean, these are the equations at the end you would get. These are the Boltzmann-Hamel equations, which are equivalents of the Lagrange equations for non-holonomic systems. These would be for three equations. These are for the shape degrees of freedom, and these would be for the scale. Yeah, and here the k is the curvature of the connection form which we defined before. So it's the exterior derivative of the connection form which we defined, which we used before. Yeah, that's where the k comes from in this equation. But these are the general equations for the n-body system. So equations of motion for the n-body system expressed in shape degrees of freedom, shape coordinates, scale coordinates, and what was the last one? Shape, scale. There was one. Oh yeah, orientational coordinates. Yeah, these are the general equation, and now we want to be more specific and we work out those equations for three-body problem. Yeah, you have three bodies in absolute space. Seen from God's point of view, you have these 3 points, and then you have you can define from them 2 Jacobi vectors. Yeah, and then these are the 2 shape degrees of freedom, shape coordinates, and this becomes the lambda. So we are doing a coordinate transformation on absolute configuration space from Cartesian coordinates to these coordinates. And if you do, I'm trying to go to the next slide. Yeah, if you do the coordinate transformations correctly after some pages of calculations, you would get to this metric. Yeah, that's a straightforward but long calculation. This would become the metric for the three-body system. And then I should go to the next. Oh yeah, and this would become the Lagrangian. Yeah, again, it's a straightforward but long calculation. This would become the classical Lagrangian of your three-body system, in which V is of course this. Yeah, the V is this. In this form, you don't see that it is a function of S1 and S2. But if you consider the fact that G is a homogeneous function of degree 1, you would see that the dependence on a scale would disappear, and of course it is rotationally and translationally invariant. And in order to do calculation, we don't know which function it is, G. Yeah, we just know that it is a homogeneous function of degree 1. We just take some function which has this characteristic. Yeah, we just as a guess to do calculation to get at some concrete answer at the end, or some concrete equation. And the G is, I mean, my tablet is getting a bit slow. Okay, now it's going. So the G, we just define it as to be a square root of center of mass inertia. Yeah, which is defined like this. And this G is, we are aware of that this is not a realistic function. Yeah, for a universe which is isotropic and homogeneous like ours, the calculation of the value of G here would not this would be way too big. Yeah, this would not be realistic. But we just wanted to have some function which has the homogeneity of degree 1 to do calculation. So if you calculate that, you would see at the end, with these 3 particle system in mind, you would see that G would become like this. And then putting it together, you would have the V, which is like this. So in this form, you would see that the V on shape space, it is just a function on how do you call it, of shape variables. There is no dependence on lambda or anything else. Yeah. And this would be the Boltzmann-Hamel equations of motions, or if you wish, the modified Lagrange's equations of motion for this system, for this three-body system. And as you see, just the S's are appearing, and the lambda dot, the lambda big dot, which are the scale velocity. You can call it a scale velocity. Yeah. And we just, at the end, we just want to see some cosmological consequences of this scale invariant theory. Yeah, and one of the examples which one could think of is the Big Bang or Big Crunch. We want to look at a system which is going to a central collision, or which is emerging from a central collision. We want to see what this theory has to say about such a universe or such a system. I try to go. Yeah. Okay. These are the points. Dilational momentum d was given by this equation was a conserved quantity of our theory. Yeah. For an external observer, one can choose without loss of generality the fixed absolute unit of lengths being equal to system's scale at some moment of time, call it t0, some arbitrary moment of time. So absolute length unit is lambda at this time, t0. Yeah, and remember the duration of absolute time passed during one tick of internal clock is like this: delta t absolute is lambda times delta t internal. Yeah, so if we are at time t0, that's the time we chose our rod, for example. At that time, delta t absolute is the same as delta t internal, but at other times, delta t absolute and internal would differ from each other. And of course, we don't have access to delta t absolute. Yeah, we do have always access to delta t internal. This is from a Newtonian point of view, or from God's point of view, if you wish. Putting all this together, one sees that d absolute is lambda d relational. It's a simple calculation to see that the dilational momentum seen from absolute space or measured in absolute units is lambda times the d that you measure internally. So the total collision of system singularity of Newtonian theory does not happen in any finite absolute time in our theory. The smaller the universe gets, the slower it contracts. So this is seen from absolute space. So you think you are the God, and you are looking at the universe. You have your own non-material clock and non-material rod. And you see that this theory, in this theory, colliding or collapsing universe becomes slowed. The closer the universe, the smaller the universe become, the slower it moves towards the central collision. And a simple calculation shows that from absolute point of view, it takes forever to get to the central collision. So you would never get to the central collision in this sense. So an expanding universe on the other side must necessarily be an accelerated expanding universe forever. Yeah, this is again seen from God's view. That is just what this equation says us. Yeah, the dilational momentum, is increasing. But here there are some caveats. We do see a accelerated expansion of the universe, but what we do see is not from God's point of view, it's from internal point of view that we see accelerated, or we see things that we associate to an accelerated expansion of universe. And in order to explain that, you could think of a situation where the universe is divided in smaller parts, smaller clusters, and each cluster is being virialized, so to speak. So seen from God's point of view, the size of one cluster or one subcluster is not changing, but the distance between the clusters are changing. In that sense, you would have even access to God's rod through your own internal rod. You would have distances between, for example, Sun and Earth, which if that is the case, you would have a rod with which you are measuring actually the absolute expansion, and of course you would see you would expect to see the absolute how do you call it, the absolute accelerated expansion also happens if you use the internal measuring instruments. And let me go to the next slide. Oh yeah, that was my talk. This is a beautiful picture of Leibniz. I wanted to end my talk with this beautiful picture of Leibniz, and thanks for your attention.
Thank you, Sahand.
You're welcome. I try to close this so that I can also see the audience.
So thanks. I think this was a very interesting talk.
Thank you.
So please, we will make, I think, like a 10 minutes question, and then we should go on with the break and start again at 5. So, but if you have some question now, so please go ahead. Just raise your hands. Dustin? We don't hear you.
Yeah, thanks, Sahand, for the talk. There's a thing that a part that I think I understood and a part that I'm confused about. So what I think I understand is that you're doing something very different than Julian. You're trying to absorb scale into the constant of nature, right? So you wouldn't have all the things that Julian talked about, like
yeah, I would say I'm trying to, yeah, sorry that I'm interrupting your question, but I would say that I'm considering a scale invariant theory in that sense. I mean, with those transformation, you make the classical theory a scale invariant, and that would be a necessary thing to have from a relational point of view.
Well, but
so that
not necessary, right? I mean, because Julian doesn't do it or doesn't do it anymore, and then you have
yeah, I mean, Julian can, yeah, I understand. That's we can discuss about that, but I mean, he always himself says if you just on shape space, I mean, you need to specify the scale of the universe at some point. Just shape degrees of freedom would not suffice to say the unique evolution of the universe.
Okay, I think Julian wanted to comment on
Do
that.
you want to comment on that?
But the part or to ask about the part that confused me. So on the one hand, you used very geometric language, and on the other hand, it sometimes sounded as if you're doing like the opposite. I mean, geometry being about quantities that are, you know, independent of, or structures that are independent of coordinatization. And you seem to care very much about the numerical values of the respective quantity remaining.
I'm taking, I would say I'm taking a physicist stand to geometry, because I mean, if you speak about vectors in mathematics, those are some entities which has nothing concrete in physics. Yeah, in physics, vectors are velocities, things you measure. So from the beginning, you should talk about the measurements. If you want to put values there, you are forced from physical stance to say how you measure that. And the values come from measurements.
Okay, I have to think about that, but it's very unorthodox in some way, no? Because usually the idea of geometry is that, you know, the numbers don't matter. What is invariant?
I mean, no, I mean, you have different geometries. There are also many relationalists among geometries. I mean, you would, I think there are even Riemann himself. I mean, he was starting with some length units, and many geometers have thought about things how you measure geometry. I mean, you have to have a way to measure the geometry of a space. And if you want to look at that, I mean, you have to become some experimental physicist at some point, or take some experimental things into foundation of geometry. It is, I think it is necessary to consider that in foundation of geometry as well.
Thank you.
And I just wanted to say, because I saw David Sloan disagreeing with my comments. I have not used the dynamical similarity in any work, and I am aware of the beauty of this structure in Newtonian mechanics, that with dynamical similarity you could go further than what people have done before that. So that's another path which is beautiful, but I have some critics about that path. But I mean, tomorrow we have also time to talk about that. I mean, that's the one of the purposes of the talk.
So maybe this is a good point to move on to David's question.
I don't know if Sean wants to go first, but I'd like to say, Sahand, thanks for a very nice talk. It was nice to see.
Welcome.
I will here just voice my objection to you saying that you need to introduce scale at some point. You absolutely don't. There are autonomous systems that evolve entirely in terms of shape. And in fact, this is what Julian started off with wanting. And I think Sean's going to talk about this some more tomorrow, so I don't want to spoil too much of that. But there absolutely do exist these systems. You pay a price for it, you have to do maths a bit differently, but they really do exist and they're there.
Okay.
Aside from that, I wanted to come back to what you said about rescaling G by a factor.
Yeah.
Yeah. So, I mean, again, this is a really nice idea, and I completely agree that G has to be measured from within the system, right? We're physicists, we live within the universe, and so we have to measure all fundamental constants and so forth from within the system. I think on that we agree completely from what I understand you saying. However, again, there are actually freedoms in what you specify in this way. You've actually chosen in what you're doing here what looks very much like a dynamical similarity. You've just chosen the one that fixes mass. And in fact, there are an entire family of these that you could have chosen from, some of which would have fixed G, some of which would have fixed T, some of which would have fixed R. There's actually a complete freedom in how you do that. And
I think the difference with dynamical similarity, we come to it tomorrow as well, is the combination of the change in units of length and change in unit of time. In dynamical similarity, it is completely clear how this works. Yeah, it is also written in your papers and your colleagues. And in this way of transformation, you would not respect dynamical similarity. So it does not, this transformation fall not under dynamical similarity. These are not among those transformations.
Okay, so you're doing a purely Hamiltonian transformation now?
Yes. Yeah.
Okay, so this is just a canonical change of variables then?
Yes, because this Hamiltonian is also a scale invariant Hamiltonian. Yeah, that's also another difference with the Hamiltonian that you start with in your work. But I don't know if that helps.
Well, I mean, Sean will talk about that. I'll leave this to Sean. Sorry.
Okay. Yeah.
Okay, so Sean, maybe you can go on.
Yeah, I mean, I thought that's what you were getting at. Because you, what am I saying? Can you just say actually again, because it was hard at least for me to follow everything together. What is the actual symmetry transformation that you're trying to gauge here?
The actual symmetry transformation is similarity group. So this is a different symmetry transformation than Newtonian, normal Newtonian theory. Normal, as you know better than me, you don't have that similarity group as symmetry transformation in Newtonian theory. We have modified Newtonian theory in a way to make it a scale invariant, and in that sense, its symmetry transformation is similarity group.
But it's the similarity group acts on Q, and then but you also have an action on V and T, and I think
Yes,
you also have the coupling constants transforming too, right?
Yes, the change of coupling constants was necessary to make similarity group a symmetry group. Yeah, that's why we did that, and to implement what we called principle of relationalism. That's one point. The other point is how you change the velocities. Of course, if you look at rotation, how you change a velocity under rotation, you take a representation of rotation group which suits the number of dimensionality of the vector you want to rotate. You know, that's how you do that. And I mean, this is for the rotation, and for the scale transformations, you should also say how vectors transform. You always must say what is the transformation of the vectors, and transformation on their scale is I derived it from how you measure velocities. Yeah, you want to measure, you are an experimental physicist, you want to measure the velocity of a particle, you use rod, you use clock, and I gave you how the rod and clock change under scale transformations. Those are all consequences of those changes in G and other constants of nature, which we consider as consequences of principle of relationalism. So principle of relationalism does not leave any space for you to transform vectors under scale transformation differently than what we explained.
Okay, I was just I understand that's what you were trying to do. I was asking what, like, how they actually transform, because I couldn't remember. But anyway, maybe we could talk later and get more detail, because I'm trying to understand the details a bit better to judge what kind of theory you get at the end of the day. Anyway, maybe it's better to talk after.
Yeah, we can do that.
Well, if you don't mind, I would ask a very final question.
Yeah, definitely.
Because, well, as far as I understood, what you do is that you try to make the similarity group the symmetry group of the Newtonian mechanics. Yes. But it is not. In the beginning, it is not because of scale. The system is not scale invariant. So what you do is basically you change you scale, so to say, the G and the other constants.
Yes. Yeah.
To somehow make it the symmetry group.
Yes, in a way to make this scale invisible.
Yeah, exactly. But then you end up with a theory which is not the usual Newtonian theory. So would it be different observationally? And also by observation, you would see a difference.
I mean, in some cases, it would be different, because I mean, what kind of function is hiding behind G? It could be that it's a function of matter distribution, and if the matter distribution in the universe changes, of course, those would have severe changes in the universe, which would deviate from a standard Newtonian theory. But if we are on the right path, I don't know, you could take care of those changes there. But for the time being, it doesn't make any different prediction, because you have already these values of G also given in this new approach. But maybe in the way past, in the history of the universe, where the shape of the universe was different, or in the far future, if the shape would be different, or I don't know, if the parameters upon which the value of G depends, or the value of Planck's constant or epsilon zero depends, if those change in the universe, then you would see the deviation popping up. But as long as these values are the same, you don't see any deviation. So for the time being, I would say you don't see any deviation, but we are saying at least you can have an explanation of the accelerated expansion expanded universe from this perspective. But from the Newtonian ones, I mean, it's still a mystery.
Okay, so maybe I think this is a good point to have a break, so that we can all think about this. And we meet in half an hour again. And
Okay.
Thank you again, Sahand.
Thanks, Sahand.
You're welcome. Thanks for your attention.
Thank you.